Okay, everyone, so as we continue in 6.8, we're still just going to be solving more limit problems. So this one, we still try our plug-in, right? I've got 1 over x cubed log x as x goes to infinity. So I get 1 over infinity cubed. That's 0, right? We're literally getting 1 over infinity cubed. So 1 over infinity, that's a 0, times log of infinity, and that is infinity. We are getting 0 times infinity here. So this is indeterminate, but I can't apply L'Hopital's rule, right? I can only apply L'Hopital's rule for these two forms. So what am I going to do if I'm in this form? I need to make it into a fraction. Same thing here, everybody. All of these first two are just about making things into fractions. This is typically just getting a common denominator. This can be a little bit trickier. So it's indeterminate, but I cannot apply L'Hopital's rule. Okay? So I need to manipulate this, and it will always work, everybody. You can manipulate this so that it will either be infinity over infinity or 0 over 0. Well, maybe you're realizing I'm being a little foolish in this first one. How do you change this into a fraction? Well, why don't we just multiply it out? 1 over x cubed times log of x, well, that would just be log x over x cubed. It's only a very, very subtle change from here to here, but now all of a sudden we're looking at a fraction. So instead of looking at these as two pieces being multiplied, now we're looking at them as two pieces being divided. And that makes all the difference, because now, well, log of infinity is still infinity, but now it's not 1 over infinity cubed. Now I'm just looking at infinity cubed in the denominator, and that is infinity. So we are getting an infinity over infinity. So I couldn't apply L'Hopital's rule like this, but I can apply L'Hopital's rule like this. So now my LH for L'Hopital's, again, follow my work, indeterminate, but there's no L'Hopital's rule here. This is regular manipulation, but now I've got indeterminate where L'Hopital's rule applies. Now I'm applying that, so I still have my limit, but now I take my derivative, 1 over x over 3x squared. Be nice to yourself, everybody. Sometimes L'Hopital's rule like this was so quick and clean that we were just able to move right into the plug-in. Here, do yourself a favor, right? Clean this up. Instead of leaving this ugly fraction, multiply by the reciprocal. So I'm not applying L'Hopital's rule. This is just a little bit of algebra cleanup. I get 1 over 3x cubed. And as x goes to infinity, 1 over 3 times infinity cubed, 1 over infinity, takes me to an answer of 0. So again, go back to number 1. Infinity over infinity went to infinity. Here, infinity over infinity went to 0. I mean, we do get a lot of answers of 0 and infinity. But again, you see there's plenty of other answers that are coming up as well. So let's keep going. This one technically was 0 times infinity, but very quickly can easily make that into something infinity over infinity. Number 7, let's take a look at the limit of 4x e to the minus 3x. Again, multiplication. I don't have division. There's no chance L'Hopital's rule applies, but first things first, let me plug in. 4 times infinity is infinity, and then I get e to the negative infinity, which is 0. Infinity times 0. 0 times infinity, infinity times 0, same thing, indeterminate, but not in a good spot. Okay, indeterminate, but not one of our two preferred indeterminants. So once again, need to manipulate. Here, we got this to be a fraction by literally just multiplying, and then we had our division. So then L'Hopital's rule worked. Here, do you see one piece that might be easier to move into the denominator? This is e to a negative exponent. why don't we change the exponent to a positive by putting this whole thing in the denominator? So again, no L'Hopital's rule here. This is just algebraic manipulation. I'm leaving the 4x alone, but I'm shifting the e to the bottom, and now it's e to the positive 3x. Try and take my limit as x goes to infinity. 4 times infinity is infinity. Now it's e to the positive 3 times infinity. So I'm not getting e to the negative infinity this time. I'm getting e to the positive infinity, which is infinity. Now I can apply L'Hopital's rule. Derivative of the top over derivative of the bottom. Try plugging in. 4 over 3e to the infinity. 4 over infinity gives us an answer of 0. Let me show you a quick little thing on this problem before we move on and do another. Because here's the little catch, everybody. Either one of these could have gone to the denominator. I very easily could have had 4e to the minus 3x in the numerator and x to the negative 1 in the denominator. And now, well, this is still 4e to the negative infinity. That's 0. This is x to the negative 1. That's a 1 over x in the denominator. So that as x goes to infinity would go to 0. So this limit in this form would still get me to a form where L'Hopital's rule would work. But look what happens. You'd be in the same spot. You get minus 12e to the minus infinity, that's 0. Now it's minus 1 over x squared, but as x goes to infinity, that still goes to 0. So you're still in 0 over 0, and some people say, oh, no big deal, we've seen that. I'll do another iteration. But when you're doing multiple iterations of L'Hopital's rule, you gotta hope something nice is happening algebraically with your function. That when we did that back in that very first one, we had an x squared, that became a 2x, that 2 canceled, so just an x, that just became a 1. So we could see the powers of x going down, making it an easier function to deal with. But if you do another round of L'Hopital's rule here, you get plus 36e to the minus 3x over plus 2x to the minus 3. And there's another 0 over 0, but things aren't getting better here. The e isn't changing. You know, the e is kind of neutral. When you take a derivative of an e function, you basically get the same thing back. So that's kind of a neutral move, but these variables to a power, we're going in the wrong direction. So this is another 0 over 0, and we'd be doing this forever. So to point out, just because L'Hopital's rule applies, doesn't mean that you're just going to get the answer. You still have to see, are you making progress? And problems like this, like these two, again, you always have a choice as to what goes in the denominator. This was a little more obvious. Hopefully even this one, it's a little more natural, I should say, to make an exponent positive versus making an exponent that's already positive, making it negative. But it's not like we've never seen that before to say this has never worked. It was worth a try, but hopefully you realize, wait a second, this doesn't seem like we're making progress. Let me try moving the other one, and then one step, you've got your answer. So this didn't help. This was the way. Okay, one more like this. Let's look at number 8. Let's look at the limit. I have x approaches 0 from the right here. I'll show you why I need that in just a moment. And it's because of this. My function is x squared log x. Technically, it doesn't make sense to let x just approach 0 because you can't approach 0 from the left. We can't have negatives inside our logs. They're not in the domain. So don't let that plus bother you, everybody. That's really just a technicality to make this limit problem make sense. So don't let the 0 bother you. I plug in 0 squared is 0. Log of 0 is negative infinity. Right, we made that note at the beginning, and here I needed it. log of 0 from the right, technically, but it still takes me to negative infinity, and that is still indeterminate. Just like we said over here, the signs on infinity doesn't matter, same thing here. I didn't want to try and use parentheses to show that. 0 times any infinity. We said that in words when we wrote this, and here it is. It's not just 0 times positive infinity, like we saw here and here. 0 times any infinity is indeterminate. Okay, well, as we saw in the previous two, I can't use L'Hopital's rule here. I need to get some sort of a fraction. And now we think about what's more easy to move into the denominator. And here we just said, well, we didn't really want to make this a negative exponent. We already had a negative, so that was a little more natural. But now here, this is more natural. So this one will move to the denominator. So I'll have an x to the minus 2 in the bottom, a log x on top. Again, think of this like this when you're plugging in. 1 over 0 is infinity. Technically 0 from the right, we're getting positive infinity here, but that's not to worry. That's an infinity. Log of 0 is negative infinity. Any infinity over any infinity. That's L'Hopital's rule. So I get 1 over x minus 2x to the minus 3. Derivative of the top over the derivative of the bottom. But kind of like what we saw up here, I'm going to clean that up. I'm not going to try and plug 0 into this mess. I'm going to clean this up a bit. This is really minus 2 over x cubed, so it becomes times x cubed over minus 2. So when I clean this up, limit x approaches 0, I get 1x cancels. I have x squared divided by negative 2. And like we saw, things cleaned up. I didn't just apply L'Hopital's rule and get a royal mess. It looked messy, but by actually taking a moment and doing some algebra, this cleaned up pretty nicely. Feels like L'Hopital's rule got us to a better spot, but I know that for sure when I plug in, 0 squared over negative 2 is 0. Okay, everybody, so again, a lot of little work so far. Same thing here. If you try and put the log in the denominator, x squared log x to the negative 1, 1 over log in the denominator. Now you're getting a 0 over 0, but look at your derivative. If you apply your L'Hopital's rule, the 2x is really nice, but now look at this ugly chain rule. Minus log to the negative 2 power times a 1 over x. So, like I said, it's kind of like, okay, that is a L'Hopital's rule situation with the indeterminate form you would get from this. But now just looking at that derivative, boy, that's ugly. You may think, oh, look, I'll clean that up. But it's a 1 over x here, x over 1 here. It actually combines. It doesn't even cancel. So again, you're just making things really, really ugly and messy here. This way, it may not have looked super pretty right off the bat, but one round of L'Hopital's rule allowed for a lot of nice cleanup for a nice answer. So 0 times infinity, not the worst. They need a little bit of manipulating. Some people get into this section, they see L'Hopital's rule, they do a couple of the easy problems right off the bat. L'Hopital's rule directly applies, and they just get in bad habits. They don't check what indeterminate form they're in. They just take a couple of derivatives, they randomly plug in, they get some right answers, but that's missing the big point. Plugging in, seeing which indeterminate form, knowing when you get to directly apply L'Hopital's versus when you need some manipulation. And now the last bunch. Let's start with, this will be number 9. Let's take a look. The limit. Again, I've got 0 from the right. I'll point out why that's necessary in a little bit. X to the x squared power. What happens here? We plug in 0, 0 to the 0 squared power. That's 0 to the 0. indeterminate. But again, indeterminate, but another one of those situations where we cannot use L'Hopital's rule. This time, it's not just trouble, it's trouble specifically with an exponent. So what we're going to do here, this is a nice little trick, and this will be used for all of these indeterminate forms. When we're in trouble and there's some exponential trouble, right? 0 to the 0, 1 to the infinity. We are in some trouble, we have an indeterminate form, but there's an exponent involved. And again, I really hope you're clear with what I'm saying here. I'm looking at an exponent as I plug in. Not just saying, well, it was an x to the fifth. Infinity to the fifth power, again, we can handle that, but 1 to the infinity, that's indeterminate. That's what we're seeing right here. 0 to the 0, that's indeterminate. So what we do is this little trick. This is my original function y. So ultimately, I'm trying to find the limit of y as x goes to 0. But what I can do here, when I'm in this kind of trouble, I'm going to apply the log to this function. So I get log of y on this side, but when I apply the log over here, now I can take advantage of those properties. Log of x to the x squared, that exponent is on all of this. I don't want to write equals here. This is a whole new limit problem. But when I apply that log, I will have x squared times log x. Log of x to the x squared power, the x squared out in front as a multiplier. But now, as we approach 0, and this is why, everybody, I had to have 0 from the right here because I knew eventually we would need a log. And that's why that was, again, there. Don't let that bother you. Again, I'm not trying to trick you and give you bogus limit problems. That's just there to make this a legitimate question. So there's no one side that doesn't exist. But okay, now we're back to 0. And we've basically seen this one. Not just basically, we literally just saw this problem in number 8. So you'd go through, you'd have 0 times negative infinity, you'd have to manipulate to get that to be a fraction, to get infinity over infinity, to then apply L'Hopital's rule and get an answer. But here's the problem. So again, everybody, all of this work right here for number 8 is now going right here on this second line of number 9. Here was my first part, realized I was indeterminate, so I applied the log, and now here's my second part. So I do all of that work that we did on number 8 to get that answer as 0. So I'll even keep that in the notes so you don't realize that didn't just come from thin air. That came from the previous problem. But realize why we're not done. What we just found is the limit of log of y. So if log of y goes to 0, we want to get back to plain old y. That was the original function. This was the original limit that we care about. How do we undo the log? Raise both sides e. Notice we're applying the inverses. We applied a log at the beginning of the problem to get something we could handle, but at the end we have to counteract that log by taking in the e. And e to the 0 gives us 1. This final answer is 1. This is actually very, very similar to the logarithmic differentiation. You're taking advantage of the properties of logs. So when we had ugly functions that had lots of multiplication, division, exponents, you took that log so you could break that function up and make it more simple. And that's what we're seeing here. We're taking a log of this function to change this function, but at the very end, just like the logarithmic differentiation, you applied that log, but then you had to do implicit differentiation. You got an extra times the original function for your derivative at the end. But now, it's not even that bad. It's just simply about applying the e to undo the log and get us back to our original. So let's do 2 more like that. Let's look at number 10, the limit of x to the 1 over x power as x goes to infinity. Plug in, well, x goes to infinity, I get infinity, but I get infinity to the 1 over infinity. 1 over infinity is 0. So this is infinity to the 0 power, another indeterminate, and another indeterminate form where there's an exponent involved. So just like the last one, I'm going to take the log. So I'm going to set up a new limit problem. The log of this, and when I apply the log, that allows that 1 over x to kick out in front as a multiplier. Do you notice how I'm using the previous problems? Now, what we're left with here, and I hope you realize this is not a coincidence. 0 over 0 and infinity over infinity were preferred because we go right to L'Hopital's rule. But then 0 times infinity, we need to manipulate to get one of those first two, 0 over 0 or infinity over infinity. And now these exponents start with an exponent issue, but now when we apply the log, this becomes a multiplier. Notice what happens here, infinity, so 1 over infinity is 0, log of infinity is infinity. So we had an exponent problem, which became a multiplication problem. Same thing happened here, everybody. This was 0 times negative infinity. Now I'm getting 0 times infinity. So now I need to manipulate to get that to be a fraction. And this is what we saw. This was very similar to what we saw in problem number 6. In number 6, it was 1 over x cubed times log x, but same thing. Now, with this setup as x goes to infinity, we went from indeterminate to better indeterminate to our best indeterminate. And this one is our best because now we can finally apply L'Hopital's rule. And this one we once again get 0. But just like the last one. How do you finish this, everybody? Some people like to finish their answer right back at the top. Some people like to rewrite at the end. But you got to do something, make it clear. You're not done. Some people like to always do this at the end. They make that note. So this one, not that it always equals 0, but that's just a coincidence. But this one did. Once again, this answer, that wasn't the answer for what y approached. That's what log of y approached. So that the original function y goes to e to this power, which would be 1. But again, everybody, it's not 0 to the 0 power is 1 or infinity to the 0 is 1. These are just two examples where after we took the log, we ended up getting 0, so then e to the 0 equals 1. Let's finish with one last one. Number 11, save the toughest one for last. The limit 1 plus 1 over x to the x as x goes to infinity. Maybe that looks familiar because if you go back in section 6.2, we introduced this as the definition of e. This limit equals e. And by the way, that's worth memorizing. I'm going to prove it right now. Before, we did a little computational work to kind of verify that, and the book just kind of defined that as e. But now we can actually prove that result, not directly, but eventually through L'Hopital's rule. But just before I do that, just to point out, these are equivalents. Some people, if you get a common denominator here, and again, I'm not trying to scare you, but when we get to chapter 11, we are going to use a lot of limits. And this is a limit. I'm not going to say it comes up every, around every corner, but probably a good 5 to 7 times throughout chapter 11, this limit comes up. And this is not an easy limit to solve, so it's great to just have that memorized that that answer is e. To know in either form here, this eventually just becomes e. But again, let's prove that result. X goes to infinity, 1 plus 1 over infinity to the infinity. 1 plus 1 over infinity to the infinity. 1 over infinity is 0, so 1 plus 0, I get 1 to the infinity power. Same thing here. You could be very methodical about this, directly this is infinity over infinity to the infinity power. Use your L'Hopital's rule inside of here or dominant terms. This becomes 1, 1 to the infinity. Either way, we're in some trouble. And again, I don't want to say trouble exactly, but it's indeterminate. And out of all of them, I think this is the one that people most commonly just think is not indeterminate. 0 to the 0, infinity to the 0, those both at least seem odd enough that people hesitate, but 1 to the infinity power, people are so tempted to just say 0. To just say 1. 1 to any power is 1, so 1 to the infinity is 1. But as we pointed out back when we introduced this as e, it's not just 1. There's a little something there. This goes to 0, but doesn't equal 0. Once again, seeing the difference between approaching and equaling, that there is a distinction. So that's kind of the issue here. But what I'm going to do is, again, still in this form, still going to take the log to set up a new limit. And by taking log of all of this, just that x. Just that x creeps out in front. So now, as x goes to infinity, well, this is infinity. Over here, log of 1 plus 1 over infinity. 1 over infinity is 0. 1 plus 0 is 1, so I get log of 1, but that's 0, so infinity times 0. Still indeterminate, making progress. Indeterminate with an exponent. Now that's an indeterminate product, an indeterminate multiplication. So I'll shift one piece to the denominator. I'll put the x into the denominator. So it's an x to the minus 1, a 1 over x. As x goes to infinity, this is still log of 1, so that's 0. And x to the minus 1, 1 over x, 1 over infinity. Now we've made our full progression. Trouble with an exponent, trouble with a product, to now that good trouble that we get where we can apply L'Hopital's rule. So I'm going to finish this up here. Derivative bottom, the derivative of the top. You get 1 over this. So I'm going to cheat and use this form. Get a common denominator. So 1 over this flips the fraction. I get x over x plus 1 times the derivative of the inside. But now instead of leaving the inside like this and using quotient rule, leave the inside like this. Derivative of the inside just comes right here. Treat that as an x to the minus 1. So there's its derivative. Clean up. These cancel. Now with what's left behind, x goes to infinity. Again, you should be able to just do dominant terms and get that equals 1. But you could have an infinity over infinity and then do one more round of L'Hopital's rule. But we keep seeing we should be able to handle these nice powers of x as x goes to infinity. So this is 1. So log of y went to 1. E on both sides. Y goes to e. That's a proof of why that equals e. You could expand this when we talked very quickly about compound interest in 6.5. I made that note 1 plus r over n to the n went to e to the r power. Put any number here, it works very, very nicely. That extra number is just a multiplier right here, so you get 1 times that extra number. Okay, so lots to practice here. Thinking about your upcoming exam, yeah, there's going to be some limits, not a ton. We've got so much from Chapter 6, so everything from Chapter 6 that you should be thinking about, the derivatives of the new functions, the antiderivatives of the new functions, probably like one application of exponential growth decay, a couple of problems where you need to use derivative antiderivatives, tangent line, critical numbers for derivatives, area under the curve for the definite integral, and a little bit with limits and L'Hopital's rule. So it's easy to kind of look at this section and say, well, there shouldn't be too many problems on the test that come from here, and to undervalue its need. But like I keep saying, when we get to the end of Chapter 7, We'll have some limits, and L'Hopital's rule and indeterminate form will come up there. And then we're going to see it a lot in Chapter 11. So you want to have good practice to be ready for this right now for your upcoming exam on Chapter 6. This is included, but you really want to have lots of practice so that you're ready to use this a lot when we get to Chapter 11.